Hi all. So in the first chapter we looked at in chemistry, we looked at states of matter, and part of that we looked at was the changing of state. So going from a solid to a liquid to a gas, where you add heat, so melting and boiling, and then where you remove heat, going from a gas to a liquid, condensing, and going from a liquid to a solid, freezing. So if you can't quite remember those, maybe go back over and check to see to revise them. In the meantime, what we're moving forward with is the difference between physical and chemical changes. So those are changes of state going from melting, boiling, from solid, liquid to gas. But we have to look at the difference between physical reactions or changes and chemical reactions or changes. So in order to help us do that, we have to ask us a number of questions about the changes. So the obvious and most kind of easiest ones to look at are, well, the first one is a new substance formed? If a new substance entirely is formed, then we're talking about a chemical change. Whereas if there's no new substance formed, you're talking about a physical change. And what that means is, are the particles actually changing? So if you think about ice as the solid, ice will melt to form water, which will then be boiled to form water vapor. Those particles are exactly the same. While they have gained heat energy, they have changed physically. Their particles are moving differently. There is no difference in the substance. The chemicals that is making up the water, when it's ice or when it's water vapor, or when it's liquid water, it doesn't make a difference. The particles are still the same, so therefore that's classified as a physical change. A chemical change is one where an entirely new substance is formed, and we're going to look at different examples of that now. Okay. So if you have a look at this one, first of all, this would usually be done as a group, but obviously you can do them on your own. So if you look at the balloon, the first one there, she's blown up a balloon. So is there any new substance formed, or is that just, is it a physical change or a chemical change? So I think obviously blowing up a balloon, she's just making a change physically. It looks different. So that's a physical change. Melting chocolate or the ice, both of those would be classified as physical changes, because chocolate is still chocolate, water is still water, it doesn't matter, the particles haven't changed, no new substance is formed, so therefore they are classified as physical, not chemical changes. And the thing is with these, they're more or less reversible as well. So if you melt the chocolate or you melt the ice and then cool them back again or freeze them, they will go hard again. So there's no new substance formed, there's no change in the particles, so they're physical changes. Okay, now if we look at something like burning a match, this is slightly different, because in this, yes, heat is involved. Yes, you're talking about energy being produced in the form of heat, but number one, you can't reverse this change, and number two, you're getting different particles. If you think about the match is burnt, it's forming new particles because it's giving off smoke, it's giving off heat, it's giving off ash. They're all entirely new particles. The particles are changed, so therefore that's classified as a chemical change. So if the particles are changed, it's chemical. If you get a new substance, it's chemical. If it's not reversible, it's chemical. However, if there's no change to particles, if it's potentially reversible, or if there's no new substance formed, we classify it as a physical change or a physical reaction. Okay, so to kind of narrow this down, physical changes are changes in which no new substance is formed. They're usually reversible. Now, again, there's always exceptions to this rule. If you smash a glass, you can technically glue it back together, but it's not going to be identical. So it is somewhat reversible, but not entirely. So in the physical changes, particles lose or gain energy, but they do not change their form. So things like you growing, you getting bigger, you're still made of the same cells, the same particles, but they're changing, they're getting bigger. Crushing a can, melting ice cream, breaking glass, all of those are physical changes. There's no new substance formed, there's no changing in the atoms or the chemical structure of that. Okay. If you look at chemical changes, however, they're changes in which a new substance is formed. So they're very difficult to reverse as a general rule, and energy is either produced or absorbed to change the particles. So things like burning, anything that involves fire or flames, that's entirely new substances formed. You're giving off carbon dioxide, you're giving off smoke, you're giving off ash. The likes of fruit rotting, or that's a physical change. You can't reverse that, and you get a new substance. An apple will turn into something else, it gets broken down and put back into the atmosphere. Anything you cook, if you cook at all, if you make a mixture with eggs and butter and flour, that's just a mixture, that's a physical change. But if you actually cook it, you can't go then and separate them out. They have changed how they look, how they taste, how they feel, so that therefore is a chemical change. The same is said for rusting. So any sort of change where you get a new substance, so your metal, your iron is becoming rust, that's an entirely different change in the chemical structure, so that's classified as a chemical change. Okay, so I hope that's a bit clearer for you. What I want you to do is, as part of your work this week, is to complete this slide 49, and I want you to group together, so put 2 headings in your copy, one for physical changes, one for chemical changes, and then the letters A through I, A through L, if you can categorize them as a physical or a chemical change. Remember, always think back to the thing, is a new substance formed? Are the atoms changed? If the answer to those 2 questions is yes, it's chemical. If the answer is no, it's physical. Okay, so I want you to complete that. I'll put that up on Schoology and you can complete that for me the next day. All right. Yeah, and here's just some examples then that you can have a look at. So you can go through that when you've done it. So I would ask you to do it first and then go through slide 50 afterwards. All right. So in terms of changes when we're in the lab, obviously chemical reactions or changes are the things that we are more interested in. So a chemical change or a chemical reaction is what happens between substances. So there's numerous different chemical reactions you can do in the lab, and when you're reacting things in the lab, you have reactants and you have products. So for example, if I want to burn something, say I'm burning paper, the paper and the match that I use to light it are the reactants. That's what we start with, and the products are what we get at the end. So the ash, the flame, the smoke, the carbon dioxide that's produced, they're your products. Okay, so what you start with are your reactants, okay, the reactants, and what you finish with are the products. All right. There's a little video there. I'm going to ask you to click into that and watch it on YouTube. It gives a nice little explanation of that as well. Okay. So again, I'd usually get you to do this as a think, pair, share, but I'm just going to go through this instead. So some of the things you can expect to see during a chemical reaction are things like a color change, a temperature change, where light is given off. So if you think about fireworks, you're giving off light. If you think about a bulb being switched on, there's a reaction happening there. There's light given out. A flame, anything burning, there's light given out. Bubbles of a gas. So if you see any bubbles being produced, it's generally as a result of a gas being given off, which means there's a chemical reaction happening. Or a smell also would link with the gas. It's a sign that there's something coming off. So there, if you see any of those things happening during a change or something you're doing in the lab, it's a good sign that it's a chemical reaction as opposed to a physical change. So one example that I could do, you don't have to do it, but one example sometimes I do is showing you a chemical change. And in this, there's 2 different things that I use. There's sulfur and there's iron. Now iron, you can buy it in the lab. It comes as little iron filings. It's little silvery grey metal ground up, and then your sulfur comes as a yellow powder, and it smells a bit like rotten eggs. Is probably the best smell that you can get, or best example I can give you. So they're very different chemicals. When you mix them in together, so we put a little spoon of each of them in together into a test tube, and we heat them over a Bunsen burner. What happens is they start to go through a chemical reaction. The 2 elements react with each other when you put them in heat, and they give you a very different contents. So what you're left with is a black, solid, hard substance, and you can't separate them out. It's called iron sulfide, and that's a really good example of a chemical reaction whereby you're getting a new substance. The atoms are changed, the appearance is changed, it loses its smell, it doesn't have the same properties or the same characteristics anymore because of the fact it's performed a chemical reaction. And that's a good example which I will send you on a video link to as well. Okay, so the last little bit we're going to look at then is a thing called the law of conservation of mass. Okay, and it sounds a bit more complicated than what it is. Basically, that if you think about the word conservation, it's to keep the same. to conserve, you keep it the same. So when you're talking about physical and chemical changes, you're talking about matter, your solids, your liquids, gases, your plasma changing from one form into another, and reacting with other things. When reactions happen, you have, I'm just going to skip ahead here. When reactions happen, there's no change in mass, okay? So if you start with 50 grams of iron and 50 grams of sulfur, and you react them together for iron sulfide, you will end up with 100 grams. You started with 100 grams, you will finish with 100 grams. The same applies to every reaction that happens. If you start with 10 grams, you will finish with 10 grams. If you start with 500 grams, you will finish with 500 grams. The law of conservation of mass says that the mass of a substance cannot be created or destroyed, it simply remains constant. So if you start, as I said, if your reactants, the things you start with, are 20 grams at the start of the reaction, and then you carry out your reaction, they will still be 20 grams at the end. That's all the law of conservation of mass is, okay? So I can show that using particle diagrams. So as you know, water is H2O. So H is for hydrogen, all right, and O is for oxygen. So you start with 4 atoms of hydrogen, 4 of oxygen, and when they combine to give you water, you end up with 4 of each. Okay, so there's no conservation mass. You start with 5 grams of hydrogen, 5 grams of oxygen, and together they will give you 10 grams of water. No matter what chemical reaction you look at, whether it's H2O water, whether it's carbon and oxygen to form CO2, carbon dioxide, whether it's carbon and hydrogen to form CH4, methane, you will always have the same basic law apply, which is that the mass of your reactants, the things that you start with in the reaction, will always be the same as the things that you end with. Now you might think, like, going back to the example of burning being a chemical reaction, well, if I have 100 grams of wood and I burn it, surely I'm not going to have 100 grams left. But if you think about it, when you burn the wood, the gas, carbon dioxide comes off and the smoke, if you could contain them and stop them from floating off into the air, and if you could find the mass of those along with the ash that's left and keep it all in, you'd still have 100 grams, okay? So while it would escape if you left it, if you actually contained it and trapped it, it would be 100. So that applies to all reactions, and there's no exception to that rule, okay? So I'm just going to get you to do these couple of questions. I'll put them up as there's a few examples there. I'll put them up as an example for you on the Schoology. I'm going to ask you to work through them, and I'll put up an example for you as well. And I'm going to get you to do a few little questions for me on Schoology as well. If you have any questions on that, I will add a couple of videos if needed, but hopefully that should make sense to everyone. Okay, thanks, bye.